Starting the recording. I think it was yesterday while we were talking about the homework that I asked you where a function is continuous. If you had to explain to somebody what you understand so far about, or not where it's continuous, where it has a limit. If you had to explain the concept of a limit to somebody, what parts of a graph could you tell them to ignore? And maybe think in terms of a piecewise example. Like the one we did on the board the other day. Let me sketch this up here just for a little refresher. And it may not be exactly like it was, but it'll be close enough. All right, so remember we were divided somewhere around +1. And then like the left side looked something like, well no, it didn't do that for sure. Let's see if I can undo that. Undo, there we go. All right, so it started like went across that way and I had a hole here and then I had another hole and I know it wasn't down here but I'm going to make it there just for the sake of conversation. All right, so let's say this is my picture. Where in this picture does the limit exist? Well, let me ask a better question, an easier question to answer. There's only one correct answer to this one. Where in this picture does the limit not exist? And tell me why. At the asymptote. Well, it's not really an asymptote. Remember, that's our dividing line of a piecewise. So for this piecewise function, the limit does not exist at the break. Why not?
Because it's two sides are approach the same point.
Okay. What is the correct calculus way to say that? Carlos, what was that? That is, but I want the calculus way. Colin, you got it?
Yes, ma'am. Well, as you're approaching x from the right and as you're approaching x from the left, the values of the limits don't necessarily match.
Exactly. The limit as x approaches y, I'm sorry, as x approaches whatever this c value is. So we'd probably say c just for the sake of discussion. Let's say that that happens at c. All right. The limit as x approaches c from the left. What's the next thing that I should write on my paper? What symbol? Does not equal. So it would be an equal with a slash through it. So I could write the limit as x approaches c from the left does not equal the limit as x approaches c from the right. Now I'm going to ask you the question that will help you understand why we're starting this conversation here. Okay? Is there anywhere else on this function, because remember it was defined with the equations of the two lines for the piecewise. Y'all remember the one I'm talking about? Okay. Is there anywhere else on this function that that would be true for? Right, it's going to go all the way out to infinity as what you see here. So I'm asking you, is there anywhere else on this graph that I would expect to find a place where the limit does not exist? So what does that say from an intuitive understanding about the limit everywhere else on this graph? It exists, right? And why at a glance can you say that? Because what do you see? You see continuous pieces on each side, right? All right, so that's why continuity belongs in this chapter. Okay? Because the limit exists wherever a function is continuous. So on any interval where the function is continuous, I know I have a limit. Because if you zoomed in on any one point, you're going to say that the limit as x approaches c at that point is going to give me back the y at that point, right? And it's there because it's solid, right? Okay. Just a little background definition there. All right, so now, in fact, I'm going to go to a full screen, and that means nothing to y'all, so you can just write right underneath it. But to define, in terms of our calculus understanding now, continuity at a point. Now this is where we get into specific elements of any kind of a graph, where you know how you have those crazy pictures in 2-1 you had to look at and decide where do I have a left-hand limit, where do I have a right-hand limit, where do I have the limit, and all that stuff. Okay, so we're going to start with interior points. Now, what do you think we would mean by interior points, as opposed to what? Okay, as opposed to exterior. That's like when you go to buy paint. If you're painting inside, you don't need exterior paint, right? Okay, well, if I'm looking at a graph, in fact, thinking of those pictures in 2-1, where would you classify the points to be interior? And then there's another word, a little mathy word I'm looking for you to call up. Nothing? You got nothing? I'll tell you when we get there. All right, interior points. And I'm not going to say a function y equals f of x. I'm just going straight for f of x because we've all discussed that when I write that, that means this is a function. Yes? All right, because that's what function notation is. All right, f of x is continuous and that looks weird the way it's written, but that's correct, at an interior point C, we're calling that C, and that's universally where what we will call that particular point of interest throughout this course. And those words in your book are bold print, and that becomes really important to distinguish there. Continuous at an interior point C of its domain if the limit as x approaches C of f of x equals f of C. Now, you will evaporate all of the frustration that built up in me before we started this video today if you can answer this question. What does this symbolic definition, a statement that I just wrote, have to do with what we talked about before I started writing this definition? Loud enough for the whole class to hear, whatever contribution you have, and I just saw a facial expression that I'd better hear some words coming out of someone's mouth. Looked like an epiphany on someone's face and no sound yet. Come on, talk to me. What does this symbolic definition have to do with what we talked about before we started this? Okay, so maybe we need to back up a step. What does this mean? And I didn't read it to you for its meaning because you should know, and I want you to tell me. The limit as x approaches C of f of x equals f of C. I've read it to you now. You can quit reading it to me. I want you to tell me what that means. Yes, Trey. Say that louder so that I can make sure this little microphone picked it up.
The y value at that point is this limit.
The y value at that point is the limit. Okay? Now, what does that have to do with what we talked about before? What did we talk in this lesson? I don't mean like during the homework discussion. I mean like once I started this video. What did we talk about that connects to that very fact? Okay, what did we say about that graph that's on your paper? Let me put it back up here on the screen so you can see it. What did we say? What did we say, Todd? I'm glad you said that really quiet because I'm kind of glad it's not on the video. Anyone? What did we say about this graph? Where does the limit exist? Everywhere except at the breaking point, right? In the piecewise? Okay? And why did I say that was of significance? And why did I say that you could be assured, and why do you know that you can be assured that when you graph a continuous line, as long as you're not picking your pencil up, every mark you make on the page represents a point at which the limit exists? Why? Because there's no hole, right? At any of the points means that, well, even if there was a hole, if I pluck a hole in the middle of a, okay, let me throw another picture back up here. All right, so if I have this situation, where does the limit exist in that picture? Everywhere. Everywhere on it, including at the hole. Why? Because at the hole, what do I have that we said we have to have? The limit from the left equals the limit from the right, yes? And you don't have to say it to me in formal like you're reading the symbolic definition every time, but I do want to hear you say, when I ask you, how do I know the limit exists at this point? I want to hear you say, because the limit from the left equals the limit from the right. Right? In conversation, that makes sense, doesn't it? Okay, so then that's what I was saying when the fact that this thing has a limit everywhere, but at that point, it's because of this definition. Right? So now we're upgrading having a limit to being continuous. Are you with me? What's the difference? what's the distinction? And you're actually going to get taught this in this lesson, but you should understand it intuitively right now, especially after what we just said. What is the difference? Where, okay, in this little squiggly line with the hole in the middle of it that I drew, this particular picture, where on it do I have a limit?
Everywhere.
Everywhere. All right, now let's rethink in terms of continuity. Where on this little picture is this function continuous? Everywhere except the hole. Because the hole is, by definition, a discontinuity. Right? The intuitive understanding of continuous from pre-cal was it's continuous anywhere I draw it that I don't have to pick up my pencil. Right? But as soon as I pick up my pencil to stop, whether it's a hole or a stopping point, that means that there's some kind of discontinuity there. Right? You with me? Okay. So far, the definition says the limit as x approaches c of f of x equals f of c. All right, now, I'm going to take you back a step further because I know you don't think at this level of discipline yet. But there is a requirement here implied by this statement. What's required in order to have the limit as x approaches c to be a thing? No, just to have a limit now. I'm not talking about the continuous part. What? And I'm not saying y'all were wrong. I was saying, responding to what Will said. When do I have a limit? When does the limit, and remember I told you I'll say it with emphasis. When I say that, I mean the limit, not one of them. Right, when both sides' limits are equal, right? Okay, so that little part that I underlined right there, you should probably, and this is not in the definition because it is implied, but I know that would sneak past you if I don't point it out. So what does this require? And I'm going to switch colors to let you know that I am adding to the definition. If you look at the definition in your book, you won't see this in your definition, but it's implied. It's embedded. You're supposed to have learned that from the previous lessons, okay? So what did you say that means? The limit as x approaches c, how? From the left of f of x equals the limit as x approaches c from the right of f of x. So all of that is embedded in the statement, the limit as x approaches c of f of x, right? So if I tell you, when I make the statement, the limit, and I want you to tell me what comes into your mind, even if it's wrong, so that we can get clarity, because this is where if we can get clarity now, it makes everything easier for the rest of this chapter, all right? If I tell you, and I'm just going to write a statement, and this is sort of a break from the definition, so I'm going to switch to another screen so we won't have it in the middle of our definition. If I tell you, or you see in writing, that the limit as x approaches 1 of f of x is 7. Now tell me what you know for a fact. As the limit approaches this function from the left, the limit is 7. As this function approaches 1 from the right, 7. How do you know that? Because this says the limit with no indicator, right? No indicator means I'm saying it's the same from both sides. So every time you see that, don't forget that. Because if you don't understand that, you're going to have to retrace those steps every time and say, well, wait a minute, what does that say about the limit from the left? Well, obviously it's the same thing if you understand it. Are you with me? So that's really important that you get that straight. Now, what does that tell me? Woosah breathing for Twitty for a moment. What does that tell me about what's happening when x equals 1? No, at the point. Don't talk to me about the graph. We're just talking about a point. There's a hole? That tells me there's a hole? See, when y'all start muttering like some sort of monk, that tells me you don't really know. Okay, let's rewind. What did I tell you in 2:1? And I'm not saying y'all are having wrong thoughts. I'm just not getting enough auditory thoughts from you, okay? I believe I said, this is something you need to remember, and I said it in 2:1, and I said it again in 2:2. I've probably said it at least once every day since we started this chapter, that when we're doing a limit, we don't care what's happening at the point. In the same way, when I read a limit statement like what I've written here, I don't know what's happening at the point because of this. Okay, I know it's one of two things. For this to be true, tell me what two things are possible. There is a hole, so this implies that there is either a hole at 1,7 or a defined point there. Doesn't that make sense? So don't assume, because if you go beyond the fact that reading that limit statement tells you that the limit exists, all that tells you is that I know whatever else this function does anywhere else, the closer the function gets to 1, the x value gets to 1 from the left, and the closer the x value gets to 1 from the right, I know that I end up at the location 1,7. Whether the point there is closed or open, I have no way of knowing just off that information. Does that make sense? Okay. All right. And I'm making a big deal about that because these are the little nuances that if you don't get them straight now, you'll be fighting them all the way up to and maybe on the day of the AP exam. And I'd like to avoid that for all of us. Okay? I love you too much to watch you suffer. Hand up. Yes?
So is it safe to say, like, in that last problem you just had up there, that as...
In this one?
Yeah.
Okay.
Is it safe to say that as x approaches to 1, y is getting closer to 7?
Yes. That's exactly what the limit means. And that's kind of, in layman's terms, what you just said is basically going back to the epsilon delta definition of a limit. Okay? And I feel like I'd rather show you that sort of towards the end of the chapter than the beginning, because if I showed you that on 2-1, you'd all be saying, when is the last day to drop this class? So we'll save that for when you're more ready for it, okay? All right. So to finish up our definition, yes, you've already passed it, so don't even try it. You are trapped now. You are my prisoner from 8 to 9:30 till the first week of January. How does it feel? All right, endpoint. Endpoint was the word I was looking for a few minutes ago. Yep, Connor. We're so glad you stayed. Aren't we glad he stayed, folks? You are too smart not to be here. Okay. Okay. Now, remember a few minutes ago I said if we're at an interior point, we're somewhere on the function, and the only place we wouldn't be on an interior point. Okay, so like for instance, if I probably should have brought up the parent function, you know, that is continuous in one, is like goes to infinity in one direction, but it has a starting point. What function am I describing? Square root graph. Okay, so if I go out to the right, the limit as x approaches infinity of that graph would be infinity. Yes, it would, because it goes up forever, yes? Okay. How about when I go towards the left? Remember on the must-know functions test, a lot of you got weird about what to say when you went to the left? When you don't approach infinity from the negative infinity on that graph, do you? Because it doesn't live there. But what you do approach as you go to the left, where would you end up? You'd end up at the origin, right? So that would be an endpoint. So that's kind of a special case, because if I try to talk about continuity at the origin on that graph, if you try to fall back on your definition of limits, because we just defined continuity with limits, right? Can I say that about that point? I don't have a limit from both sides, okay? So that's why we have to distinguish and talk about the endpoint separately, okay? Again, we'll start with f of x is continuous at and I don't really like the way they do this. I'm just going to say at an endpoint, and then we'll denote which one's which. In your book, they say at a left endpoint A. Oh, no. Well, I guess I need to. All right. At left endpoint A, and that, if you think about it, that complies with what we talked about last year. With our intervals, we always used AB as our first, and we will continue to use those 2 points. At left endpoint A or right endpoint B, and again, the continuous at bit is underlined, is bold, so you can underline it in your notes, of its domain, if the limit as x approaches a from the right of f of x. Okay, would that work to talk about f of x, the square root of x? Because which way could you approach the origin on the square root graph? You have to come at it from the right. There is no left to come at it from, right? Okay, so the limit as x approaches a from the right of f of x equals, what do you think? F of a. And that's a terrible f of a, so let me fix that because that looks like a capital F. And we can't use capital Fs. That actually matters this year. All right? Kind of mattered all along, but I was trying to be patient. Or the limit as x approaches b. Well, let's just say I had the square root of negative x. What does the negative on the inside do to the function? Flips it over the other way. Okay, so now that we're talking about that graph, we're talking about its horizontal reflection, the square root's horizontal reflection. So now the limit as x approaches b, how would I have to approach that one? From the left, yes? Does that make sense? Of f of x equals f of b. You got it. So when I tell you, and I will on your test at least once, I will tell you to prove that the limit, that the function is continuous at a point. Some function is continuous at some point, some x value. Then your job is to show me three things. What three pieces do I have to put together and must all be equal for continuity at a point to exist? And now we're talking interior. It's a three-part requirement on interior. It's a two-part at an endpoint. What would the three-part requirement to prove continuity at a point be based on this definition? Okay, say it louder, guys, because I'm hearing it muttered. The limit from the left must equal some value. You must show that it equals some value, and then you must show, that's part one. Part two, the limit from the right must equal some value and must equal the first. Because if it doesn't, you can stop. You don't need the third part because you've just proved it's not continuous. Because if the limit from the left does not equal the limit from the right, we have to have some sort of jump there, don't we? Okay? So then what will we say? Let's just say that the limit from the left equals the limit from the right. What's my third part? What do they have to equal? F of c. So what do I have to do? I have to plug the c I'm approaching into the function and demonstrate that the y value I get is what? F of c, which it is by definition, has to equal. So what would my left and right-hand limits have to also equal? F of c. Does that make sense?
Yes.
Okay. Whew, y'all are working me to death here. All right. Okay. So now we've talked about continuity at a point, and these are actually going to be easier because we're going to define these in words. Okay. The most important thing in this lesson is the definition we just went over. If you don't get that, you're going to struggle for a while. And yes, I said struggle. Okay. The struggle will be real. All right. Continuous. And I would imagine if you have not done either of the homework assignments in this chapter so far, that you're probably struggling a little bit today. That's what happens when you let it pile up behind you. You come in unprepared to think on the level that I'm going to require you to think in our conversations. All right? Continuous on an interval. Okay? A function, FCN, universal abbreviation for the word, is continuous. On an interval.
Thank you.
If and only if, which we write as if with two F's, which we learned in geometry. If you didn't, learn it today. If and only if. Now this is going to sound silly, but then I'm going to ask you what it really means. If and only if it is continuous, and I'm going to erase that because I'm not going to have room to finish it. So I'm going to slide down here and get a pen back instead of an eraser to write with, continuous at every point on the interval. Now, does that sound silly? Because your English teacher would have a problem with this definition. Why would your English teachers have a problem with this definition? Because you used the word continuous to define continuous. Okay? But what did we just define? Before this. Continuity at a point, right? Which is a three-part requirement. The limit from the left has to equal the limit from the right, has to equal the function value there. So they all have to equal f of c for it to have continuity at that point, right? But clearly, we don't want to have to prove point continuity for every function we'd never finish, right? So we have to agree, for discussion, that if you are so basically what's going to happen is, if I tell you f of x is continuous on the interval 3 to 7. So what happens in your head? You don't know what happens at 3. You don't know what happens at 7, because I didn't specify, right? But what do you know? You do know that the function has to be defined, the limit from the left has to equal the limit from the right, has to equal the function value there all the way across the interval. You get all the points on that interval for free when you're given that information. So this is more of when you read, if a function is continuous on this interval, then it's going to ask you some questions. You see what I'm saying? So you got to understand what that phrase actually means. All right. Now we're going to talk about a continuous function, which we actually talked about last year, and I'm just going to write this as a statement and make it a little less writing to have to do for all of us. A continuous function is one that is continuous at every point in its domain. That also sounds like not much of a definition because it seems kind of obvious, right? Okay. Well, I'm going to show you two functions from your parent functions that you need to think about for this definition to have its full impact, okay? Quick sketch of the inverse function, 1 over x. Oh, that's terrible. Even for a quick sketch, that's bad. All right. Just a little refresher. That's what 1 over x very roughly looks like, yes? Okay. Is this function, which you should be drawing on your paper right now, is this function continuous?
No. Yes.
Or let me rephrase that more specifically. Is this a continuous function? I'm getting no's and yeses. I need a no person to tell me why you're saying no. Colin?
Well, I'm saying that it's no, because when you're approaching 0 from both the right and left, it doesn't necessarily have the same value.
Oh, no, we can be more emphatic than it doesn't necessarily. It clearly doesn't have the same value. But if I approach a function from the left and I approach a function from the right, am I thinking continuity or am I thinking about something else? I'm thinking about what word that this chapter is dedicated to. Limits, okay? The limit from the left doesn't equal the limit from the right, okay? But listen to the definition as I read it to you from the board. A continuous function is one that is continuous at every point in its domain. So what would be a crucial thing to ponder before I answer the question whether this is a continuous function? Let's talk about the domain of this guy. What is the domain of this guy? Negative infinity to 0, parenthesis, union, 0 to infinity. Okay? So as long as it's continuous on those two intervals, we're good, right? Is it? Yes, it is. This is a continuous function because it is continuous everywhere on its domain. Right? And if you think about trying to apply the definition of continuity at a point, and you went to apply the definition of continuity at a point for 0, It's going to fail because it's outside its domain, right? Okay, now we're going to look at another one, but I'm only going to go into the first quadrant, and I'm going to switch colors so that you can see the step that I need to show you. I'll go with this light green and see if that works. So there's a step here, a step here, a step here, a step here. Now, and just so you don't freak out, we don't use the step function much other than to think about things like limits, okay? We're not going to be doing a lot with the step function, but it's one that helps you think, all right? Remember, these steps all look like you got a closed dot on the left and an open dot on the right. Now, I'm not going to take the time to put those on there, but every step, the dot to the left is closed, the left endpoint is closed, and the right endpoint is open, right? Okay, and that's important to think about. All right, now, this is one that almost inevitably students get wrong when we talk about it, but what is the domain of the step function? It's negative infinity to infinity, right? Doesn't look like it, but it is, because everywhere I hit a right endpoint that's a hole, what's directly above it? A left endpoint that's closed. So this function is defined for every value you can give it, right? So the domain of this one is then all real numbers. So the domain runs from negative infinity to infinity, but what do we clearly have within that domain? Let me rephrase that. How many discontinuities do we have? An infinite number, right? So everywhere on it that I could find one of those points, like here, right, at where I go from one step to the next, I have a jump discontinuity, yes? So that means that although the function is defined there, the limit from the left equals the integer to the left, and the limit from the right equals the integer to the right of that joint, right? So this is not a continuous function, because read the definition again. It is continuous at every point in its domain. So at all the integer values, the step function is discontinuous. So in an infinite number of places, this one fails to be a continuous function. So continuous function, check. Continuous function, no. Right? You with me? All right, we will stop there because that's as good a stopping place as we're going to get. And I will tell you that we will pick back up with page 80. If your book is open, and you don't need to open it for this, it's not worth the trouble if you haven't already got it open. This will be very familiar. This is where we discuss the discontinuity types. I jumped over that to get to the continuous on an interval versus continuous function. So we'll come back and refresh our memory on those discontinuity types and then close out with the rest of the lesson. So here's what I would like for you to do. I would like for you to look at the first few problems on the assignment. Actually, the first few problems on the assignment are pre-cal. So you should be able to do them anyway. So start the assignment, see how well you do, and then when you hit something we hadn't done before, like the intermediate value theorem, stop. Because what I'll do tomorrow is I'll start with questions from whatever you've accomplished when you get here tomorrow and finish with the notes, okay? And don't worry, at some point you'll get to take that quiz.